and gravity. So, for example, the energy in thermodynamics corresponds to the mass of the black hole. The temperature in thermodynamics corresponds to h bar times the surface gravity over 2 pi. Up to Boltzmann's constant, it's really kBT corresponds to that. And the entropy is a quarter of the horizon area. I've put in the h bars explicitly, but not Boltzmann's constant or Newton's constant. So this analogy came out from what I said in the first session, and there are arguments behind that, one of which I'll review in some detail, but modified for black hole chemistry. But one of the things in this analogy that's conspicuous by its absence is this term right here. So in normal thermodynamics, if you went to a chemistry class or worked in a chemistry lab, you'd say a change in energy was equal to the heat, temperature times the change in entropy, plus work terms, but there's also a VDP, a volume times a small change in pressure. For example, if you have a gas and you crush the box of the gas a little bit, the pressure goes up, and that changes the energy of the system. And everyday thermodynamics has this all the time. But for decades, there was no such term here. People thought maybe it doesn't really matter very much. These were understood to be work terms. This is electric potential times the change in charge, and this is the angular velocity of a black hole times the change in its angular momentum. And you can add corresponding terms here for electric potential, or maybe rotational energy, or chemical potential, or something. But what the heck is that? Black hole chemistry began by appreciating the importance of this term. And you might think, well, what's the big deal? It's just another term. It turns out, actually, there is an awful lot contained within this, as I hope to show you as this proceeds. So let's first review some basic thermodynamics. We have the concept of an equilibrium state, which is the state of a physical system that doesn't have any macroscopic change. Like the air in this room, the individual molecules of oxygen and nitrogen and carbon dioxide are whizzing like mad, bouncing around, but the air in this room is basically the same. It has what we would call a common temperature. We would say that, to a very good approximation, the air in this room is in an equilibrium state. And a thermodynamic system is basically a system that has a family of these kinds of states. We see that when we want to turn the heat up and down in the room. If the room is cold, it's in one equilibrium state. We want to change that state by making it warmer so we can turn on the heaters, and after a little while it would progress to this new equilibrium state. And so these states are parameterized by, first of all, the energy, the total energy of the system, and then a number of other conserved quantities. Angular momentum, if it has any, though that's not very common. Pressure, if it has any, that's the big thing in black hole chemistry. But charge and others. There's usually a few conserved quantities within any equilibrium system. And then, of course, we have external constraints. In this case of the air, it's the walls and ceiling and floor of the room. Is everybody okay with that? So, the idea of equilibration is a system evolves in finite time toward equilibrium, or toward an equilibrium state. And the work done is the change in the energy of the system, which is the energy that it costs you, or the environment, if it's a non-directed process, that implements the change. For example, I've got gas in a box, and I have a piston, and I can make the box smaller. Well, I will raise the energy of the gas in the box, but it costs me energy to push the piston in. Conversely, take a balloon. I have a balloon at equilibrium, but if it's too big, or let's say if I pop it, I get lots of energy coming out because the balloon explodes. Now, I may not be able to use much of that energy unless I want to entertain little kids, but that's the basic idea. So the laws of thermodynamics, well, the zeroth law is the notion that temperature is constant at equilibrium. In some sense, equilibrium is what allows us to define a notion of temperature, which is effectively a kind of average energy. And there are different ways of getting at this. We say that two systems are in two systems that are in thermal contact, which means they can exchange heat, are jointly in equilibrium if they're separately in equilibrium at equal temperatures. In other words, temperature is what we use to label an equilibrium state. So if I have a liquid here, and I say it's at 30 degrees Celsius, and I have a liquid here, and I say it's at 30 degrees Celsius, then when I put them together, it's going to be at 30 degrees Celsius. That's the whole idea, that temperature can label what the equilibrium state is. Whereas if I have water at 2 degrees Celsius and water at 30 degrees Celsius, and I put them together, well, for a while, it's not going to have a well-defined temperature. But if I wait a little bit, it'll establish a new equilibrium where the temperature will be somewhere in between those two. So the whole point of this is that two systems in thermal equilibrium with a third one must be in thermal equilibrium with each other. This is in some sense what we mean by the zeroth law. The next one, the first law, is conservation of energy. That the change in the total energy of the system is the heat minus the work on it. Heat is work, work is heat. So the change in energy is the heat you supply it minus the work the system does. So for example, if I have a box of gas and there's a piston, I can heat up the gas and then the gas will expand doing work on the piston, pushing it out. So that would be an example of this. The change in the energy of the gas would be the heat I supplied from the fire, or whatever I was heating underneath it, minus the work done. And the second law is that entropy never adiabatically decreases, where adiabatic means an operation that takes a system from one equilibrium state to another without coupling it to other thermodynamic systems, or in simple terms, there's no heat flow. So I could do work on it, but I'm not allowed any heat transfer, or rather the heat transfer has to be negligible. And entropy will never decrease when that happens. That's basically the second law. Entropy stays the same or gets bigger. So we can characterize this by saying the entropy is a function of the total energy and all these other extra quantities that are conserved quantities in the system, and this second law basically says that. So here we have this. So if I make a small change in the entropy, simply because of this functional dependence, it's going to equal a constant times a small change in the energy plus other constants times small changes in the other parameters. And that constant beta is the inverse temperature, which I'm sure you all know. Beta is 1 over T. So the first law is usually written by inverting this equation to put the change of energy on the left-hand side. And we say it's T ds minus all these other terms, which we call the work terms. So this is the energy flow into the system from a reservoir, or it can be understood this way, like the example of the gas with the fire underneath. The fire is like the reservoir giving heat to the gas, and T delta S is what that heat is. And then all the rest of this stuff are the small adiabatic changes in the parameters. Maybe I added a little more gas to the system when I did this. That would be a change in the number of particles, and there would be a chemical potential for that, for example. So, simply by normal calculus, 1 over T is the partial derivative of S with respect to U, where all the other parameters are held fixed. These lambdas, by this equation, are the partial derivative of S with respect to each x, where all the other x's and u are held fixed, multiplied by 1 over beta, which is what we call the temperature. And so temperature can be defined as di S di U with respect to x, and each lambda, each lambda is called the conjugate variable with respect to x, and that's just could be given by du. This one is upside down. This should be du s. Sorry about that. I could try and fix it on the fly, but maybe I'll go ahead. Sorry. This one's right. This one's upside down. This should say this should say beta, or this should say du ds. My apologies. So what you get is, here are some examples. If x is the volume, lambda is the pressure, the conjugate to the volume, or vice versa. If x is the momentum, lambda is the center of mass velocity. If x is the angular momentum, lambda is the angular velocity. If x is the charge, lambda is the electric potential. If x is the particle number, we call lambda the chemical potential. And we could do a magnetic, well, if there were such a thing as magnetic charge, we'd have a magnetic potential. So, what if we have lots of systems? Well, I already mentioned this notion of thermal contact. What it basically means is when two systems are in thermal contact, everything is fixed except the heat flow. So you hold somebody's hands that are cold. Try it now if you want. You hold somebody's hands that are cold, heat will flow from the warm hand to the cold hand, but nothing else is changing. The general notion of contact between systems is when more can change. You could have heat flow, but you could also have other conserved quantities. Charge could flow back and forth. You could move the system and give it momentum, and so on. And multiple systems, to the best of our knowledge, can be treated as one system. If I have two boxes of gas, I could put them together side by side, and I could consider that one complete system if I so decided to do. And the second law holds for multiple systems. If it holds for each system individually, then you can show it has to hold for those two systems considered as a single one, and by extension this works for anything. And what that means is, unlike what happens with one system, this fixes entropy up to an overall scale at an additive constant. Everything I said on the previous slide, I could have taken some other function of entropy and redefined the temperature and the other conjugate variables. But if I impose that this be true, then I can't do that anymore. Once I've decided what the entropy is, the only freedom I have is to add an overall constant to it, and I can rescale it. I can multiply it by 2 or a half or something. But I have no other freedom of definition. I can't use s squared anymore, or the square root of s, or some other function. So the notion of, we also have in thermodynamics, and this is quite important, often forgotten, I think, in black hole thermodynamics and seldom looked at, is this concept of local equilibrium. And that happens when one subsystem equilibrates faster than the rest. For example, we have it today. It's a bit cooler in this room than it is outside. This room is at thermal equilibrium. Outside is at a different thermal equilibrium. What's preventing the two from equilibrating is these walls. They're providing insulation. So here we believe there's a very good notion of thermal equilibrium within this room, even though the university as a whole is not at thermal equilibrium. The same can happen with the sun. There are parts of the sun that equilibrate faster than the others, and this is what allows, for example, for convective flow of hot chunks of hot junk moving upward through the sun. The chunk of hot stuff is at one temperature, it's at one state of equilibrium, different from its surroundings in the rest of the sun. So what that means is that the thermodynamic quantities will depend on where you are in the system. Are we in this room? Are we outside? So let's suppose we have two systems together and some heat flows between them. Well, the change in entropy of the whole thing is ds1 plus ds2, the sum of the changes of the entropy in each one, which is simply the amount of heat going out of number one divided by its temperature, plus the amount of heat, the same amount of heat going into number two divided by its temperature, because by definition, dq is T ds. So if you combine these together, just factor out dq, the total entropy, the change in the total entropy of the system is this heat flow times this product of temperatures. And now we can see the importance of temperature. If the two are equal, there's no change in entropy. They're both a system at thermal equilibrium here, at the same temperature as one at equilibrium here. You put them together, they're still at thermal equilibrium. There's no change in entropy. But otherwise, this has to be positive. What does that mean? Well, what it means is we never see a situation where you can get heat going this way, but this guy is bigger than that one. In other words, if that were true, then you'd get heat going from a cold body into a hot one. But instead, we always see heat going from hot to cold, right? When you hold the hands of a cold person, your hands get colder and theirs warm up. That's why you do it. You never see it go the other way around. Not without the addition of extra work into the system, which is what gets me to the next point. So this means that T1 is greater than T2, that's just what I said before. Equilibrium by definition is when the T's are equal. That's the zeroth law. So now let's take these two systems, but let's put a machine in between them. And we're going to let this heat flow, but the heat flows into the machine an amount Q1. It flows out by an amount Q2. And I can extract work from this if Q1 and Q2 are not equal to each other. In fact, by conservation of energy, what comes out of this has to be the sum total of what goes into T2 and what I pull out of here. So one can define the notion of engine efficiency, which basically is the ratio of the amount of work you get divided by the amount of heat that went into the engine in the first place. And that's simply, by this equation, 1 minus Q2 divided by Q1. And then I use these relations up here to get 1 minus T2 ds2 over T1 ds1. And because of the second law, this is always going to be less than or equal to 1 minus T2 divided by T1. So if the temperatures are equal, I have zero efficiency. I can't get any work out of two systems that are at equilibrium. The best would be if this could be an actual zero. Then I'd get perfect efficiency. But of course, in everyday life, I have something in the middle. T2 is colder than T1, but I'm not going to get any more work out of it. It's not going to be any more efficient than that ratio. And that all is a consequence of the second law, which comes from that. So that's all a reminder of basic thermodynamics. And what's funny about black hole thermodynamics, especially when we get to black hole chemistry, is these concepts can all be applied there. Most recently, we won't see that today, but this notion of engines efficiency has recently been applied to black holes. So let's put in gravity. Gravity and thermodynamics is very strange, and it still has a lot of some basic unsolved classical problems. When I have a gas of stuff, molecules, they bounce off each other. The short-range forces are repulsive due to electromagnetism. Gravity is not like that. Gravity is always attractive. So unlike other systems, when you have gravitating things moving around, they tend to clump together. You can therefore get long-range forces, unlike what you get in everyday thermodynamics. If a bunch of stuff clumps here, it will form effectively a heavy mass that affects stuff over here, over a much longer range than ordinarily would be the case. So it is not known if even a one-dimensional self-gravitating system approaches equilibrium under general conditions. People have done numerical simulations, and in fact, it's not conclusive. So one-dimensional gravity, you can put a bunch of particles on a line and they're each attracted to the others by a constant force. That's the same as the gravity in this room. We learned from first-year physics, right? There's a constant force pulling that thing down to a very good degree of approximation. If you look at that system, you find it is chaotic for small numbers of bodies, and for large numbers, no one really understands its basic statistical mechanics of thermodynamic behavior. Let's look at this kind of thing for a box of radiation. So suppose I have a box that's shaped like a sphere and it's got a bunch of radiation in it. The box has radius r. And let's suppose that this box is a whole lot bigger than what it would be if it were crushed into a black hole. It's a lot bigger than its Schwarzschild radius, like the Earth. The Earth is huge, its Schwarzschild radius is about that big. We have the Stefan-Boltzmann Law, that the density of energy is proportional to the fourth power of the temperature of the radiation, and likewise we have this formula for the entropy that comes from it. It's 4/3 the volume of the box times this factor here. Basically, this is density times volume times the other factor. Now, you can treat this, even though it's heavy, provided this condition is true, people have shown that basically you can treat this pretty much as a normal thermodynamic system. If that weren't true, we wouldn't be able to understand the heat of the sun, which is a pretty heavy object. It's a gravitating object, its gravity is not negligible, but it's much larger than its Schwarzschild radius, and you can show you can treat a star, like the sun, at thermodynamic equilibrium, and if you get a bit fussier, you can look at the local equilibrium of convective things, as I said before. But once the box gets to be about this size, about 2.5 times its Schwarzschild radius, then things go strange. The sphere becomes increasingly inhomogeneous. The radiation will get a lot denser at the center than it will at the edges. It'll get, therefore, much hotter at the center than it will at the edges in a non-negligible way. The mass will no longer equal the integral of the density over the volume of the sphere. Now, we know this is true in general relativity anyway because of the curvature of space, but if you're in this regime, those effects are negligible. In this regime, they are not negligible. You can no longer scale R and M to get the same kind of sphere. So the mass of the sphere will go like the cube of its radius times the density. So if I double the radius of the sphere, I can increase the mass by a factor of 8, and in this circumstance, I'll find the basic thermodynamics doesn't change. But in this circumstance, it does change. And finally, you can show the heat capacity decreases to 0. So once you have very heavy gravitating objects, you cannot take even normal thermodynamics for granted. So one of the problems you have is, how are we going to put gravitating systems into thermal contact?
This is solely if you change the equation of state, right?
Sorry?
So if you modify the equation of the state, you can still do...
Well, that's one thing you can do, but it's not obvious immediately how to do it, so people make, like for things like neutron stars, you make conjectures and do that. The only point of that slide is to show, is to point out that for large gravitating systems that are far from the Schwarzschild radius, normal thermodynamics pretty much applies, even though gravity can't be neglected. But for neutron stars that are close to their Schwarzschild radius, then what you say is right. You've got to change things. You'll still have all these problems. One of the problems conceptually, how do you put two gravitating systems together?
So sorry, again. So this means that the concept of thermal equilibrium doesn't exist for a neutron star?
Not in, well, I'm going to get to that indirectly by this, but not in the same way. I mean, the heat at the core will be notably different than otherwise, for example. Other questions? Okay, how do I put two systems in thermal contact when their gravity is not negligible? If I've got a big box and a smaller box, if I put them too near each other, they'll tidally distort each other and actually fundamentally change the external conditions and constraints on the boxes. So it's not clear how you can do this in a way that we could with normal boxes of gas. Well, there is a way of doing it, and it's like so. Suppose I have a bucket, an empty bucket, and it's at some distance, little r, and this will be its redshift factor away from this object. I'm just putting that alpha there so you know what it is. If I lower this bucket near the first object, I can open the bottom and take in a little bit of radiation. And then I can lift that bucket back up to where it was, and that entire process is going to cost me this much work. I gain something from lowering it in, but the energy of the radiation adds a little bit of weight to the box, so it costs me more to pull it back up. And the net effect between what I gained and what I had to use to pull it back up is that I have to do that much work to get this much radiation. Now I'm going to move it over to be near the other thing. I'm imagining these are far enough apart that their gravity is negligible. I had to draw them close together, otherwise I'd run out of room in the slide. So I bring it over here, and now what I'm going to do is I'm going to compress this thing, and I'm going to compress it by this much. I'm going to decide, suppose I know both of these temperatures. I'm going to do an amount of work on it. I'm going to compress the volume by doing this much work on it. And I don't really care what the new volume is. What I care about is that this is the amount of work I do. And then I'm going to lower this thing again. And then to lower it, I gain some work because I go down in the gravitational potential. And that's the amount of work I gain from doing this, which basically you could get from that by modifying the alpha 1 factor. So the total amount of work, this costs me something, this costs me something, I get something out of this. When I add them all together and you do the arithmetic, you find this is what you get. So this can give a kind of Carnot cycle where I can transfer thermal energy from this gravitating system to that one, at least in principle, by using this mechanism of moving buckets. And in fact, I could do something a little bit different. I could change step 3, so instead of lowering the bucket all the way to the edge, I could lower it part way, right to the point where instead of getting this number, I get 0. So I lower the bucket part way, and then I open it and let the radiation fall the rest of the way. That doesn't cost me anything. So I actually can, in principle, transfer heat from here to there without costing me a nickel's worth of energy or a peso's worth of energy at all. So any questions about that? The point of this slide is to show you that there is no obstruction in principle for two gravitating systems to be in thermal contact whilst maintaining the integrity of the system and not gravitationally distorting it or messing it up. That's the idea of this. So any questions about that? Okay, so in other words, if I lowered the bucket to the middle and then let the radiation fall down, I would have heat transfer with no work, which is exactly what I want for thermal equilibrium. Remember, thermal contact is when you get heat transferring without changing anything else. This shows this is possible for gravitating systems. Now we finally get to black holes.
I don't quite understand the last step when you said that you will lower the bucket until the point where you can just release the radiation.
Yeah.
Because then there's also some work there in that process, right? So when you say that you just release the radiation, and
No work to me.
Yeah,
It costs me work to lower the bucket, and think of them as rocks. I gain energy by lowering the bucket to the first thing. I pull out a rock, I lift it up, that costs me more than what I gained. Then I move it over, and I'm going to squash the rock. I guess I shouldn't call it rock, the liquid or something. I'm going to squash the system. That costs me work. And then I can do it in such a way, I mean I can avoid step 2 really, But I can either do it in such a way that when I go back to the edge, I get a kind of Carnot cycle that depends on the temperature ratio, or instead of lowering it all the way, I lower it part way, then I open it and the junk falls in, but that costs me nothing. All I want to do is gain enough energy here to offset the cost in energy for the first two steps. And I can do that. That's all I'm trying to point out. And what that means is I can put two gravitating systems in thermal contact without doing any other external work or changing anything else. And this concept is important because without it, it's not clear we could make sense of black hole thermodynamics. Now, how you would do this in practice, of course, well, it's not my problem, I'm a theorist. But the point is, in principle, it is possible to do. That's what I want to stress from this. And we often make assumptions in black hole thermodynamics about what we can and cannot do, particularly a notion, perhaps, of thermal exchange or contact. So we could do it by this indirect route. That's all I'm trying to say. Is that?
Yes, somehow.
We will be passing through some non-equilibrium states when it free falls.
You mean the radiation?
Whatever rock you clump together and you allow it to free fall after a certain time.
Well, if the radiation is small enough, then it's like adding a little ice cube into the Pacific Ocean, right? It's not going to change that much. It's as long as it's small enough, you should be fine. If I extract a large amount of energy, then that won't work. But then I've changed. I don't want to extract so much energy from the first system that I've significantly changed its gravitational
I
effects.
when you go and lower down that, allow it to free fall, like you leave it part way. Then when it free falls, you no longer have control. So you are not like moving it quasi-equilibrium kind of way.
But it doesn't matter because it's in free fall. It just gains the point is it costs me nothing. So yeah, sure, it'll add energy to the extra system that's different from what it might have done before, but I don't care. The point is that I've transferred heat energy from one to the other without doing any other work. So for black hole thermodynamics, the basic idea is black holes are thermodynamic systems just like the gas in this room or a star or an ocean or something else. And the equilibrium states are what we call stationary black holes, the example of which is the Kerr solution or the Kerr-Newman solution. It has d by dt is a killing vector and d by d phi, and maybe some other ones as well. And other kinds of black holes that are non-stationary, maybe ones that are absorbing radiation or ones that are doing other things, accelerating perhaps, they're non-equilibrium states. And the conserved quantities associated with them come from the no-hair theorem, M, Q, and J. And in higher dimensions, you can get more Q's and J's, as we will see as this set of lectures unfolds. So here to remind you again is this Kerr-Newman solution. I like to repeat equations on slides since I can't remember what they look like, so I don't think I could expect you to either. This would be an example of a very general stationary black hole in 3 space dimensions at one time, with this electric potential and these are the other functions. So this metric that describes a black hole would count as an equilibrium state. That would be the idea of this proposal. So what I want to do now is show you how the first law of black hole how black hole mechanics comes about, but modified in a way that's suitable for what we call black hole chemistry. The original argument was given by these 3 guys, Bardeen, Carter, and Hawking. It was David Castor, Surya Ray, and Jenny Trashin who modified it in the way that I'm going to tell you about now. So the idea is, as I said last time, we have a hypersurface, some slice of space, time, in other words, space at a particular instant, It has a time-like unit normal. It has a metric on the surface that I call S, and the relationship of S to the full metric of all of the space-time is given by this relationship here, where this normal vector U dots into itself to give -1, and it's orthogonal to S. Now I can write a vector, and this is going to become a killing vector, as some function times the normal plus another vector beta that is intrinsic to the hypersurface at the next instant, and we call that the shift. And the physical interpretation, and n is called the lapse. So n is -xi dot u, and beta is called the shift. So the idea is you have a space-time, maybe a rotating black hole that's evolving, or black holes crashing, or who cares, who knows. The idea is that space's geometry at a particular instant, at the next instant, this point here is moved forward in time by n dot u, but doesn't stay in the same place in space, it gets moved over. The most common example of this is a rotating black hole, which literally drags space around it. So you can't sit still at one point without doing extra work to counterbalance it, and if you get too close, you can't even do that. But if you just think you're sitting there, you'll get pulled in the space around with the black hole, and the shift vector describes by how much that happens instant to instant. There's a quantity K called the extrinsic curvature, which basically tells you how much space is warped. So this tablecloth has 0 extrinsic curvature, but if I lift it up like this, then you can see it's bent and warped. And that warpage, this is what we think of curvature as being in everyday life, that warpage is basically how the normal vector of this sheet changes as I move it from place to place, and that's what K is telling you. How warped is the hypersurface in the larger space? How warped is this tablecloth in the larger three-dimensional world, or whatever this is? And there is another quantity called the conjugate momentum, which was derived, to my knowledge, first by Adler, Dazer, and Misner, the famous ADMs, they're no one now. And what they did is they looked at Einstein's theory, and they discovered that these quantities, n and beta, were never determined by the field equations. They had no evolution, and they functioned analogous to the gauge parameter in electromagnetism. They corresponded to choices of coordinates. The physical quantity was S, and the Einstein equations could be understood as telling you how S evolves in space, from time, how S evolves in time, depending on what stress energy and initial conditions you put into the system. And S could be understood as a position type variable. Pi is like its conjugate momentum. So just the way I could describe the motion of this remote control as having a position Q and a momentum P, I can describe space as having a metric S and a momentum pi. How many have encountered this before here? Okay, a few. How many have never seen it? How many are afraid to raise their hands when I ask them a question? Really, how many have, I didn't know how new this would be for people. A couple have seen it. Okay, so the Einstein equations can be broken into these pieces, and I'm going to consider them, and I'm going to consider that I have a black hole and that I have at least one killing field, so xi obeys this condition here. And then I'm going to consider solutions that are perturbatively close to the original solution to the equations. And while the original solution has some symmetries, the perturbed one doesn't have to. So here's all that stuff again. I'm going to evolve the system along the killing vector, and you can show that you can do that using this Hamiltonian to evolve time, n times the quantity h plus beta dotted into this vector ha, which is understood as the momentum. And the way you get those things is like so. H, by definition, is negative twice the Einstein tensor dotted twice into the normal of the hypersurface. And you can show that this is a constraint equation. It has no time evolution. If you recall that pi is like momentum, this is like a p squared, and a potential is equal to a constant, which is the cosmological constant, which I've included in this problem. Remember, maybe I should go back. I hate going backwards in slides, but I have a cosmological constant in the Einstein equations, so when I use this, this is what I get. So this is like an energy balance equation. The kinetic energy of gravity plus the potential self-energy of gravity is equal to this constant, which is another form of energy, the cosmic vacuum energy. This is obtained by dotting the Einstein tensor once into U and then projecting it back into the surface with S. Remember, S is orthogonal to U. S dot U is 0. So S is like a projector. If I take any vector and dot it into S, I get the component of the vector. Any vector dotted into S, I get the component into the surface. I'm desperate here. I use my body as a... So this is a momentum constraint. If you look at this, this is like saying the momentum of gravity is conserved. It's divergenceless. Ultimately, there's no momentum coming in or going out of the system. This is called the energy constraint, the momentum constraint, or the Hamiltonian constraint, the momentum constraint. This is very general. It doesn't care about what kind of metric you have. This is completely general. Now, what I want to do is vary the initial data. In other words, I imagine, just the way I said, S is kind of like a position. It's like on a hypersurface, it's the initial structure of space. Pi is its initial rate of change of that space. So that's the initial data, and now I'm going to perturb them a bit. I'm going to say, well, instead of this nice space here, I'm going to wiggle it a bit. This is a lot, but I'm going to wiggle it a touch. And likewise, it's momentum. And so you can show, there's some arithmetic here, which I'm not going to go through every step on, but you can then now perturb this. Remember, I don't perturb the lapse or the shift because they don't live in the surface. You can show that the change in this Hamiltonian is given by a total divergence, which when you work it out looks like that. And it's a bit of work to work this out, but you know, it's not too painful. Try it yourself. I mean, if you're in physics, your social life is probably, you know, so you might as well do it, right? Yeah, kick this guy out. Okay, so in other words, the point is this variation is the total divergence of this quantity B, which is contingent, on these changes here and implicitly on xi. So, what I'm going to do that's different is I'm also going to allow that to be perturbed. I'm going to say I'm going to consider a new hypersurface with new momenta, but possibly in a different cosmic vacuum. Well, here's what I said before, that this total change in H is a divergence of something. Well, it turns out that when you perturb this, you get minus 2n delta lambda, and this is kind of like a Gauss law, once you work out what B was and multiply by n. Now, this object, remember, is a Killing vector. It turns out on mathematical grounds, because it obeys Killing's equation, I can write it as the divergence of some quantity omega CB, where C and B are omega is antisymmetric in C and B. It's called the Killing potential, and when I do this n I think actually now is an error. That should be out. I don't know how that got there. Oh, sorry, it did. It got there from here. When I pull this out, I get this equation right here, which I think is missing this lapse. I'm sorry. So if I imagine a black hole on this hypersurface, and I take some surface outside the black hole, here's the edge of the horizon, I can now integrate this equation, like so, and I find, by the arguments I showed earlier, that this is conserved. By Gauss's law, the integral over the volume on the inside is the integral over the outside surface minus the integral over the inside surface, which I'll take to be the edge of the black hole, and so I get this thing, where B implicitly depends, B depends on xi, this quantity is this quantity, and I get 1 at each end of the black hole, where R is a normal vector. It's actually going to be the radial unit normal to these surfaces. So there's that equation again. Now suppose I take xi to be d by dt plus some constant times d by d phi. So I've got a time symmetry and I've got an azimuthal symmetry. I imagine I've got axial symmetry. Well, by definition, as I said last time, the mass is associated with this kind of surface integral with d by dt. And the angular momentum is associated with the surface integral when I replace xi with d by d phi. So I can interpret the left side of this equation when I put this thing into here. It turns out this is linear in xi, so the omega factors out. So I can use these to interpret the left. What about the right-hand side? Well, if I make omega equal to omega at the horizon, then I can define, this turns out to be the killing generator at the horizon. In other words, this is the symmetry which at the edge of the event horizon moves a point along the event horizon. So if I do that integral, it turns out you can show that's a small change in the area times the surface gravity, times 2. I'm now going to interpret lambda as minus 8 pi delta p, and I'm going to call that a pressure. I'm going to say that the volume is given by the difference between these two integrals here, and when I do that, I get the first law. And in fact, I've subtracted off a term that allows for a rotating frame at infinity. You don't have to do that, but it's sometimes convenient to. So, this term, when you have d by dt, gives me delta m. This term, when I put this term here into there, from angular momentum, I'll get omega delta j, which gives me that term. Delta A comes from the right-hand side of the equation, and the volume comes from taking this difference, and I get that. Bardeen, Carter, and Hawking got these terms here. This is the new term that makes black hole chemistry what it is.
But this term is very different than the other term, right?
This one?
Yes, because here you have the variation of like integration constant, and then you have the variation of constant of the Lagrange. Like you make the variation of the electric charge.
You are right, and we're going to see more of this. So in some sense, this is different. It's the idea is there's a number of ways of understanding that I'm not going to go through all of here. But the simplest way of understanding it is that yes, I'm varying not only the initial conditions of the metric, but I'm also varying the initial, if you look at lambda as stress energy, I'm varying the initial stress energy. And I'm going to motivate more why this should be called pressure in a few minutes. But you're right, this is the new element. That's exactly right. Sorry? I'm getting to that. Be patient, that's coming.
So I have another question here. You know that typically when you do thermodynamics, delta Q, like the transfer of heat, depends on the path. So it's path dependent.
Yes.
When you do like for the Schwarzschild solution, you get that E delta S is actually a total derivative. This is equal to delta M. And this is independent of the path.
Not always. I'm gonna, later on, we'll look at heat engines and you do get non-trivial cycles.
Okay.
You can, but for now, I gotta postpone that question till later in the week. But, yeah,
How is related this value with the physical volume of the black hole?
I'll get to that too. You're asking great questions, all of which I'm gonna get to. But I just want you to see this argument, this term, and this term are Bardeen, Carter, and Hawking. This is the new term from Castor, Ray, and Trashy. So let's look at this. There's the first, you get the first law of, that's the first law of black hole mechanics. When you make these identifications that came from Bekenstein and Hawking, then you get the first law of black hole thermodynamics. Now, there's a bit of a problem in that these two quantities here are actually both divergent. This and this turn out to give you infinity. However, you can fix this by adding and subtracting a background ADS killing potential. So remember, these two terms, this one and this one, were added together with the delta lambda. So if I add a delta lambda times an omega for ADS, and then I subtract it from here, then it turns out that both of these are finite. And you have to adjust this to get rid of the infinity here, but the adjustment you make to kill the infinity there exactly cancels the infinity in this part here. So in fact, you can construct a well-defined first law of black hole mechanics or thermodynamics, and it includes a pressure volume term. And this is where this has come from. Why was there no pressure volume in original black hole thermodynamics? Because there was no vacuum energy. The point here is that if you have vacuum energy, you must get this. I can partly address Andre's question in this way. Suppose I had electromagnetism. Then I would not be in the vacuum. I would be in the electrovacuum, and I would consider solutions of different charge as well as different initial spatial metrics and their momentum. And I would get a first law that contained charge, changes in charge. So in that sense, changing lambda, where to go, changing lambda or pressure is really conceptually no different than changing charge. Yeah?
So what happened with the action when you add that kind of terms? Because
Nothing, because I'm adding and subtracting in this, let me go back here, which I really don't like doing because I never like it when other people do it. I'm adding an omega here, and I'm subtracting it there. There's nothing done to the action. This is simply adding and subtracting the same thing to this relation. This relation is unchanged. I'm just giving a different definition of mass that makes what I subtract to make the mass finite, I add to make the volume finite. That's all that's done. Okay, so somebody asked about the SMAR formula. Sorry, go ahead.
it's not exactly the same about charge, because charge it's not in the action, you know, while lambda is constant in the action.
Yeah, we get that a lot. You can actually, so here's another answer, you can actually describe lambda as the conserved charge associated with a gauge 3 form, to use the technical language, or a 4 form potential. In other words, it's kind of like, it's the charge associated with a kind of Maxwell field strength, but instead of the Maxwell tensor having, or the Faraday tensor, I guess it is, instead of it having 2 antisymmetric indices, it has 4.
This Brown Teitelboim.
Well, Teitelboim actually talked about varial lambda to begin. It was actually Jolyon Creighton and me that first put it into the first law in 1995. What we didn't do was think about what pressure was, and that's what other people did after. Well, I'll get to some of that. But you're right. I have done it as a constant in the action, but that is not necessary to get this result. It's just easier to show.
So you say that when you put a P form, everything goes, it's straightforward to
Well, if I'm in D dimensions and put in a D minus 1 potential that has a D form field strength, I can do this, yes.
So it's the same.
Yes.
Okay.
The full details actually have never been fully worked out that way, at least published. I've done some, I mean, I keep meaning to do something on that, but I keep getting distracted by other stuff.
Sorry, Professor. Is there any way to do this in a Lagrangian formulation?
What do you mean by that? Like,
No, because we are using a Hamiltonian formulation.
oh, I see. Instead of a, that is a good question. I would not, I mean, in principle, I don't see why not, but I don't believe anybody's tried it.
Because, for example, from the common formula, you cannot obtain something about the lambda. As Marcus said,
Yeah.
you know that the lambda in the equation of motion is constant, so you cannot obtain nothing from there.
Well, yeah, but remember, the thermodynamics is different. I'm comparing one solution to a nearby one that's linearly related, that's perturbatively related by varying metric, conjugate momentum, and lambda. So I'm not doing exactly what you said. But could you look at this from a Lagrangian perspective? Yeah, I believe the answer is yes in principle, but the details, as far as I know, have not been fully worked out. So let me get to the Smar formula. Larry Smar in 1973 noticed around the same time as Bardeen, Carter, and Hawking a rather curious relationship between various quantities for a black hole. To give us to make this concrete, here's a metric, a spherically symmetric metric, and if it's a Schwarzschild black hole, V will be 1 minus 2m over r. The energy is given by the mass, which is half the event horizon radius. Set V to 0 and solve for m in terms of r plus. The temperature is 1 over r plus. The entropy is a quarter of the area, a quarter of 4 pi r plus squared. And what Larry Smar noticed is that m is twice Ts. You can probably do the arithmetic just by looking at the screen. All of this is fine, and this was a curious relation for a while, but what actually people noticed after the year 2000 is this fails if you have an ADS black hole. So here's the metric function if you have a negative cosmological constant, where lambda, I don't think I wrote it on the slide, lambda is negative 3 over L squared. Well, the energy can be calculated, and you get this. You can use counterterm methods or some other method. That's the mass. The temperature, this was known by Hawking and Page in the early 80s, is that. The entropy is that, but this relationship fails. It's not hard to check. Just do it. It does not work. So Smar doesn't work here. And this was a puzzle for a while, but it is resolved once you take into account that lambda can be a thermodynamic variable. And you can get that from scaling arguments. This was pointed out by Caldarelli, Cognola, and Clem, whose name unfortunately got split in half. Sorry about that. Around the year 2000, where they noticed you could apply Eulerian scaling to basic black hole thermodynamics. So suppose you have a function that has this property. It's a function, let's say, of 2 variables. You can have as many as you like. But suppose you have a function of 2 variables, x and y, and if you rescale x by some power of alpha and y by some other power of alpha, and you find the whole function rescales like so, then by taking the alpha derivative of both sides and setting alpha equal to 1, you get this relationship right here. Now, in general, we have these kinds of scaling relationships. In d dimensions, the mass of a black hole scales like length to the d minus 3. The area scales like length to the d minus 2. The angular momenta scale like length to the d minus 2. The cosmological constant in any dimension scales like 1 over length squared. And the charge scales like length to the d minus 3. So, if I believe in basic black hole thermodynamics that the total energy is a function of these basic parameters, I can apply Euler's argument. So this is a postulate from black hole thermodynamics. I can apply the Eulerian scaling argument, and this is the relationship I get. dm dA is what I would call the temperature, apart from this factor of 4, because this is the definition of the entropy. The electromagnetic potential is dm dq, where everything's fixed. The angular momentum is dm dj, when everything else is fixed. The pressure, by definition, is minus lambda over 8 pi. Now here's the relationship with L. The volume, then, is minus 8 pi dm di lambda, and this becomes the Smart relation. Notice you need this term right here. You need a pressure-volume term. And you can show for every black hole, I have yet to find a black hole that has a negative cosmological constant that does not obey this relation. You will find in the literature people claiming there are Smart relations that are not like this, and especially when you get to things called Lifshitz black holes. I might do this a little bit at the end, I haven't decided yet. But in any event, you find people getting other relations where these coefficients are different, that every time that happens, it's because they've either directly or most often inadvertently exploited a particular relationship between pairs of quantities here. They're usually unaware of that, and they've accidentally exploited a relationship between here and here that gives them different coefficients. So, here's the first law. When you integrate that up, you get the Smart formula. In some sense, the Smart formula can be understood as the integral of the first law, given the definitions of temperature and volume and electromagnetic potential and so on. So, for example, let's go back to that Schwarzschild ADS black hole. Let's do it in d dimensions. So this is what V would look like in d dimensions when d is 4. This is 2m over r. M tilde is just what I call the coefficient of this term. Here's lambda. So there it is again, just so you don't have to remember it. The mass, when you calculate it, is given by this quantity, The entropy is given by a quarter of the area. Omega, by the way, is this area of a sphere in d dimensions. I've written the formula here, so I'm sure most of you have it memorized, but you might have friends that don't. So, the temperature is given by this, pressure is this, volume is that. Let's check. Delta M. How am I going to vary? Varying M means varying L and varying R plus. They're the variables in the system. So delta M is, if I vary this with respect to R plus, I get this thing here. If I vary with respect to L, I get that thing right there. If I take T delta S, well, delta S is easy. It's just D minus 2 times R plus to the D minus 3 delta R plus. Here's the temperature right there. V delta P, well, delta P is easy. Delta P is minus 2 over L cubed delta L times this coefficient. And now, if you're good at doing PowerPoint arithmetic, if you can see it by your eyes, if I add up these things together, I find agreement. So the first law is satisfied. Now that's no big surprise, but notice this extra term comes in. If delta L is 0, if I say, Rob, man, you moron, cosmological constant's constant, don't you dare vary that, well, I'll get the normal first law. There's nothing wrong with fixing delta L. What I'm trying to say, or delta lambda, What I'm saying is there's nothing wrong with varying lambda. This is the new element in black hole chemistry.
What happened in theories like Einstein goes for the end of lambda?
Be patient, I will get to that. But not today. You'll have to wait till Thursday or Friday. Probably Thursday I'll do it, yeah.
Sorry, can you still define this concept of thermodynamic volume in the case of asymptotically flat spacetimes?
Give me a moment, okay? The answer is yes. What it means is not clear, but the answer is yes. So, here's all that stuff again, so you don't have to remember it. Now let's check SMAR. D minus 3 over D minus 2 times m is just replacing that coefficient with that one, so that's pretty easy. Oopsie daisy, not too fast. Ts is just this times that, so I get r to the d minus 2 times L squared over r plus, which is that term, and I get r to the d minus 2 times r squared over r, which is that term. I get minus 2 over d minus 2 PV is just this times this, where the d minus 2 is cancelled out. And if you add these together, brush my teeth and call me Smiley, you get the SMAR relation. No, you would not. Now this is where it's crucial. You can freeze lambda in the first law, but you cannot in the SMAR relation. You will not satisfy the SMAR relation unless you consider lambda this way. Okay, any questions so far? Well, you've had questions. Any other questions? So what the heck is this pressure? Well, as I said earlier, Jolyon and I actually did incorporate it into the first law way back in the mid-90s. We did not think about pressure or its conjugate variable, and then we sort of left it alone and went on to other things. In hindsight, that was probably pretty stupid of me, but there you go. Padmanabhan, about 7 years later, considered it, but it was Brian Dolan in this paper in 2011 that really tried to suggest this should be considered as a physical variable. I mean, Jolyon and I said it could in principle, but we just developed a formalism. We didn't really look at pressure. So let's look at a four-dimensional Schwarzschild ADS black hole. Here's all these parameters again: temperature, entropy, pressure, volume, etc. So here's the SMAR relation. D is 4, so D minus 3 is 1, D minus 2 is 2, and the PV term is always negative 2. Here's the first law. They're both satisfied. We just showed that. Einstein's equations, well, this is how I wrote them, but if I pulled this over to the other side, and I wanted to, sorry?
Normally there is delta energy is equal to delta Q minus PdV, right?
You could do it the other way.
So then the PV goes to the mass?
Yeah, you would redefine the mass that way, that's right. But here I've done it this way. I'm going to talk about a little what that means in a moment, but yes.
It is not the enthalpy in that case?
It becomes the enthalpy. That the mass actually is reinterpreted as enthalpy. You guys are anticipating everything I'm going to say. But yeah, the mass in black hole chemistry is enthalpy. I'll talk about that in a bit. So, so what was I saying? So if I rewrote this equation like so, and I demanded this look like a perfect fluid, I could say the vacuum is a perfect fluid. Now, cosmologists have known this for decades. If I write a perfect fluid tensor, then this can equal this if rho plus p is 0 and p is negative lambda over 8 pi. So in fact, pressure is a natural thing to consider from a cosmological perspective. And if you had a negative cosmological constant, it would behave like a positive pressure of a vacuum. Now, the weird thing, of course, is you'll have negative energy density, because rho plus p has to vanish. But that's the nature of the cosmic vacuum. If lambda were positive, then the pressure would be negative. That's what we call tension. And it seems we live in a world of cosmic tension instead of cosmic pressure. But I'll probably talk about that at the end of this set. So, there's nothing particularly out of the ordinary by considering lambda as pressure. You even get the 8 pi. So, mass, to get to the comment here, is now interpreted as enthalpy for the reasons that were just said a few minutes ago. V delta P. Temperature is surface gravity, entropy is horizon area, and now the first law is complete. There's a V delta P on both sides of the equation, unlike what has happened in traditional black hole thermodynamics since the 1970s. What the heck does this mean? Well, if I look at it this way, remember, from the cosmological vacuum fluid perspective, P is negative rho. So the mass is kind of like the energy minus rho v. The enthalpy, remember, is the energy plus PV. If I let P negative rho, the mass, which is the enthalpy, is E minus PV. What does this mean? Well, it's not too different from normal chemistry. In normal chemistry, you not only have the energy of the system, there's also an energy cost into putting a system in an environment. If I take a box of gas and put it in this room, I've got to push the rest of the gas out of the way. That's why I get enthalpy instead of energy. The same is true here. The total mass of a black hole is its original energy minus the energy of displacing the vacuum. Now, this is infinite, but I can make that finite. And so that's a qualitative explanation as to why mass should be understood as enthalpy in black hole chemistry. If you have a real vacuum or a cosmological constant, then of course energy is mass, is enthalpy, and there's no distinction. But that's because there's no vacuum to displace. But if you have a vacuum to displace, this is what's going to happen. So what is this notion of thermodynamic volume? Well, the answer is not fully resolved. Geometrically, we had this definition. We had the integral of the killing potential minus its ADS value at infinity minus, again, the integral of the potential at the black hole horizon. Thermodynamically, it's the partial derivative of mass with respect to pressure holding everything else fixed. And if you have a four-dimensional Schwarzschild ADS black hole, you can show the volume from either this definition or that one is, curiously enough, the geometric volume of the black hole, which was quite intriguing when it was first found. It's as though the volume of the black hole is what you would calculate in high school, 4/3 pi r cubed.
So, does this, all this works also for planar black holes?
Yes, it can. I'll talk about non-spherical black holes later in these lectures, but yes, the answer is yes. But what I don't want to do is mislead you and say this is a general principle. It is not a general principle. It turns out not to be true once you have rotation. And that's why I put in the Kerr ADS black hole earlier. If you take this metric, I've turned off the charge to make life easier. This is the Kerr anti-de Sitter black hole, where now this function delta is a bit more complicated. And I have other parameters like this. It turns out when you compute the volume by these methods, you do not get this quantity, you get this more complicated thing that actually depends on the angular momentum, or alternatively, it's a more complicated function of A and R plus. But that's maybe not too surprising. The area, this area is that area, the horizon area is likewise more complicated for a rotating black hole in EDS. So what is the, I didn't properly animate the whole slide. What does this thing mean? Well, it can be related to a puzzle in geometry which asks the question, if you give me a closed curve, what shape must it have in order that it encompasses the maximum amount of area? Anybody know the answer? Yeah, it's a circle. Right? If you give me a closed curve, I can make it like a rectangle or a triangle or some other funny shape, but if you ask me to encompass the maximum amount of area, it's going to be a circle. Likewise, you have a generalization of this to any closed surface. If you give me any closed surface in any dimension, and I want to ask what shape must it take to enclose the largest volume inside, the answer is it's a surface of a sphere in that dimensionality, or in one less dimension, I guess. So, that's what that is. And so you can construct this quantity R, which is the volume times d minus 1 over this parameter omega d minus 2, that's the unit area of a sphere, and divide it by the area, both exponentiated this way, so this is a unitless quantity, and you can show, geometrically, this is never larger than 1, and it equals 1 when you have a spherical surface. This is a spherical volume, that's a spherical surface. Now for black holes, a conjecture was made by Svedich, Gibbons, Kubiznak, and Pope, in this paper here. Pope's name got split too, sorry. All black holes obey this inequality, backwards to that. So they called it the reverse isoparametric inequality. In other words, if you take that to be the area of the black hole, if you take that to be the thermodynamic volume, then they conjectured this would be true. And at that time, all known black holes obeyed this property. We now know this is not correct, that this conjecture needs qualifications. What does it mean? You know, I've got all these. So here's the black hole thing. My animation's all out of order, so I'll just put everything up. So this is what it would be for a black hole, exactly the same thing, but you put in the thermodynamic volume and the area of the hole. For a four-dimensional Kerr ADS black hole, this is what it looks like. It's this horrible mess that depends on R plus, the rotation parameter A, and L squared, where remember lambda is minus 3 over L squared. You can show this is always greater than or equal to 1. Just plot it in a computer if you don't believe me, or take derivatives if you want. And it equals 1 when A is 0. And that gives a physical interpretation for this that's very general. If you tell me I've got a black hole with this thermodynamic volume, the black hole that gives you the largest entropy is the Schwarzschild ADS black hole. And any other kind, if it's rotating, you have less entropy per volume. So that is, I think there is still something to be understood about the significance of this, but I'm presenting it to you to show this volume actually means something, and we will return to this later on. How am I doing here? I think actually, well, I'm almost done. I got about 10 minutes left, but basically this is the last thing I wanted to say today, so I'll stop here and take other questions.